Now here, you see, it takes all the running you can do to keep in the same place. If you want to get somewhere else, you must run at least twice as fast as that.
Published in 1871, Lewis Carroll's Through the Looking Glass provided the inspiration for the name of the Red Queen hypothesis, which provides an insight into the evolutionary origins of sexual reproduction. William D. Hamilton was one of the first to formulate the Red Queen hypothesis with respect to parasites. In his 1980 publication, he used a simplified mathematical model to show that with a high intensity of natural selection, such as that imposed by a rapidly evolving parasite, sexual populations have the advantage over similar asexual ones. But what gives sexual populations that edge? In asexual lineages, offspring are clones that may be slightly different from their parents by random mutation. However, the same mutation occurs in the parasites, which typically have a shorter generation time. Though the asexual hosts run quickly, they do not run quickly enough to escape their inevitable fate of parasitic infection. Sexual hosts, on the other hand, are not forced to wait for slow mutation rates in order to generate variety in their offspring. Because offspring of sexual parents contain some of the genes from each parent, which are often different from one another, sexual hosts can quickly produce a variety of characteristics or phenotypes in their offspring. The variety produced is so great that the parasite's mutations, despite their rapid generation time, are not fast enough to successfully invade the host. Turns out the best way to run as fast as you can is to shuffle.
If organisms are always competing for resources, then those species that can increase their population size most quickly will have an advantage. In order to have sex, you need two sexes, a male and a female. However, males cannot bear their own children. This limits population growth in species with males. As we can clearly see here, having males in your population drastically slows how quickly a population having sex can grow. This is because males cannot bear offspring. This is known as the twofold cost of males. Men are like lava lamps. Fun to look at, but not very bright.
You might find yourself asking, if sexual reproduction is better because of the Red Queen effect, but clonal reproduction is better because of the twofold cost of males, then what happens in real life? Well, Green and Mason asked the same question.
Using a computer program, Green and Mason simulated host mutations of 10 loci. The black line represents the adaptation score of the sexual host, while the red represents that of the clonal host. An adaptation score just tells us how well adapted the host defenses are in a certain population. In this simulation, the host mutation rates were held constant, while the parasite mutation rate got faster and faster. As we can see, for either clonal or sexual, adaptation scores of hosts decline as parasite mutation rates increase relative to those of the host. On the left side of the graph, host and parasites are mutating at the same rate. At this point, neither sexual or clonal populations are at an advantage. However, on the right side of the graph, as the parasite is able to mutate faster than the host populations, the sexual host population has the advantage. At this point, hosts are maladapted to the parasites, but sexual populations are able to better keep up with the parasite than our clonal populations. To be even more realistic, Green and Mason factored in the twofold cost of sex in a sexual population, shown by the green dotted line. This cost lowers the adaptation score for the sexual population, putting it at an immediate disadvantage. We see that clonal populations are actually more fit than sexual populations when the parasite isn't mutating much faster than the host. However, a transition point exists past which sexual fitness exceeds clonal fitness. At this transition point, which is completely plausible, the parasite mutation rate is such that neither the clonal or sexual populations are better adapted. We can see here how fast parasite mutation rates could promote the success of sexually reproducing host populations, even when they are handicapped by the twofold cost of sex.
So that was a model. Now let's see a real-life example.
In a fishy experiment, sexually reproducing top minnows in two types of asexual top minnow clones were exposed to a parasite which caused black spot disease. The frequency of infection in the clones was much higher than that of the top minnows. Why do you suppose this is true? The Red Queen is at it again. The sexually reproducing top minnow is able to adapt quickly to combat the adaptations of the parasite, avoiding disease, while the clones develop adaptations at a much slower rate, thus contracting black spot disease much more often than their sexual counterparts. This is shown in the graphs on the screen. As you can see, in the pool study, the asexual clones contain more parasitized larvae per unit body length than the sexually reproducing minnows. By looking at the mathematical results and its applications in top minnows, we can clearly see that the pressure of the red queen induced by a rapidly evolving parasite outweighs the twofold cost of males and favors sexual reproduction over the production of clones. So even though the Red King was completely useless and spent the entire book sleeping, the Red Queen is a better runner for having him around. Biological theories like the Red Queen effect are applicable in many different disciplines, even business. Let's think of the company as a living organism. In order to stay alive, or in business, companies have to constantly come up with new products and services. Once one company develops a new idea, others must come up with comparable ideas to stay ahead. Both companies have evolved, but no one has gained a competitive advantage, and they are basically running in place. Sound oddly familiar? The Red Queen effect is everywhere.
It's time for some sexercise.
Come on, boys, you can run in place too.